All right, my name is Dale Forrest, and I've been working at Asana almost 40 years, but another year to make my 40-year pin. And done a variety of things in that time, both for in space and in aircraft. Currently, I'm mostly working in aviation, but I'm supporting some of our space people as well. I'm going to share my screen now because I have to do a presentation here. And I'm going to talk quite a bit about our microwave amplifier research. That overlaps considerably with your interest, I know. In fact, some of it actually was used in broadcast engineering. The Glenn Research Center at Lewis Field, they got that because they wanted to rename it for Glenn, but they still wanted to honor the Dr. Lewis, who had been the head of the NAACA research for a long time. Glenn has started out as an NACA center, particularly specializing in aircraft engines just before the US entered World War II. It was founded. And basically worked heavily on aircraft engineering for many years, which tended to develop then on into rockets as well, and later on into all sorts of areas in NASA's thing. The hangar is there because we actually have a direct taxiway to the airport. And at that one time, we had quite a few aircraft flying out. Right now, I believe we're down to none. We had the last S3B that flew, and that flew off a little while ago to San Diego for a display there at one of their museums. We have another one in the process of purchasing another aircraft for doing our research activities. I myself, this is a rough agenda. I'll talk mostly about, I started out initially was hired to work on traveling wave tube amplifiers. So discussing some of their basic and related areas of research and some of our achievements and some particular efforts we have that were directly applied to broadcasting. This is a schematic on the traveling wave tube. The amplifier is typically when you include the power supply because traveling wave tubes operate at 5 to 10 kilovolts, and hard to get that sort of DC voltages out of anything else. There are vacuum tubes with operate by an electron beam. We've done a lot of work on developing cathodes, and sometimes just teach people how to use the old ones. There was an old says the old ones, if you ran with them, they were hot. If you ran them hot without strong positive voltages, they burned out very rapidly. The new ones don't have that problem. So you can turn them voltages on and off really fast. This one describes a typical helix structure that actually travels so that the microwave beam is slowed down to match, basically pretty much exactly match the speed of the electron beam is traveling down the tube. And generally it's split in two, because otherwise you get vibrations back causing it to go into oscillation. And since even with the newer techniques, we've really increased the thing. Used to be a few percent of the power in the beam would go into the RF. We've got up more like 10, 15% now. But most of the energy is still in the electron beam when it leaves the tube, and it goes into the collector, which is operated with different electron energy, different voltages, so that the low energy ones are collected here, and the higher energy ones go on through here and recover as much energy as possible. Those with familiar with some of the broadcast electron tubes will recognize that basically they just use a different form of the electron RF interaction. So one of the projects we worked on, we were just finishing that up when I started at Glenn, was on a klystron, applying these same techniques to klystron collectors, which saved about half the power. And PBS got an Emmy for this. I'm not sure exactly why PBS was chosen. As I understand it, the technical work was all done at what was then Varian and at Glenn. Along with most of the funding was supplied by them, although the National Association of Broadcasters, the National Association of UHF Broadcasters, and PBS also gave some money. To support it. And I don't know why that happened. There. Then went out of slide mode there. I particularly tended to work on collectors. One of the things we did was change the material. The early collectors were made out of metals like tantalum, which basically produces many electrons come back off the collector elements as they come in. So you have to be very careful in your design to catch those. We developed graphite forms. Initially, we used pyrolytic graphite that may be used in the ones that were used on the klystrons, because there you can hold them so that any little speckles of graphite that have come off. Pyrolytic graphite is formed by breaking down methane on a surface and basically form a plate. So it's got a lot of gas trapped in it. And whenever you try, it tends to come off in little flakes. And in a space tube, they then float around until they short out to one of the high voltages. They are then vaporized, but basically the tube turns off. And you should be able to turn it back on. The one person I knew that actually heard of actually flying one was a Japanese group, and they didn't have the ability to tell the traveling wave tube to turn back on after it shorted out, that quite a quick short out. So their satellite basically was dead after that. We now actually use a different form. It's basically mined graphite that's treated, ground up, and then cemented back together again and baked out. And it works very well. And flies on a lot of them, is also used in a lot of the military, and I'm sure some of the commercial ones that are around, because it is simply better for the collector, better collector elements than the metals or such do. We at one time actually were trying diamond as a diamond surface, and it turned out diamonds actually are the best at creating secondary electrons known. I believe they are now used in some photomultiplier tubes and possibly some magnetrons because of that. Strange thing just on how the structure is. Graphite works beautifully and diamond works the opposite. Now, my various tubes I've worked on have flown on many different NASA missions. This is the tube we developed for the Cassini 32 gigahertz tube that was used for radio science. The collector I designed for was also used actually on the 8.4 gigahertz traveling wave tube that was used for sending back the communications and the radio data. And this actually was used to look for gravitational waves at a much lower frequency than LIGO does. So it's actually still the best proof that the low frequency, best evidence constraining how strong how much the gravitational waves there are at low frequencies, but did not actually detect any. And then, however, test general relativity and made a lot of other scientific measurements. And this is a picture of Saturn. Cassini was eventually deliberately crashed into Saturn to make sure it didn't contaminate any of the moons. The X-band tubes from Cassini were flown on the Deep Impact mission, which NASA sort of set off fireworks on July 4th, about 20 years ago or so. Now, I actually was up in Michigan, in a rural area of Michigan, and was able to see the dust cloud shining in the sunlight from that. So this is the farthest thing that humans have done that you can see from Earth. Subsequently, I worked on a lunar reconnaissance orbiter. This is overall somewhat smaller in size and about 4 times as powerful as the Cassini tube was. And all the pictures you've seen from the lunar reconnaissance orbiter have come back through this TWTA. It has some other systems they can use for command and control, but they're so far down a thing they couldn't carry any significant amount of the data they collect. Right now, they use over about 60% of the time that they're in view of Earth to transmit all the data in a white sands where they have the antennas that receive it, transmitting the data down. This is a photograph LRO took of the Apollo 11 landing site. So you can see we left some trash behind. They also actually used LROs to take many other pictures that's been used to look at where the Chinese, the landers and rovers are. The attempted Indian and Israeli landings. They see where they landed, but they weren't landing gently. So they sort of where they smashed into the moon. There were some problems with their landing techniques. It also photographed the LADEE satellite, the Lunar Atmosphere and Dust Environment Explorer. That's kind of blurry, but you can see it does show up well with the artist picture of the satellite. It was flying considerably lower, so it was between LRO and the moon. And as I understand, it has since crashed. LADEE has since crashed in the moon. LRO will eventually, but it is still taking more data. Previously back in the 70s, we worked with Canadians on communications technology. We call it the Communications Technology Satellite at NASA. They called it Hermes. It was used to do to remote locations, broadcast televisions to typically community TV sets of there. But it was also considered to have done the first direct-to-home broadcast, broadcasting the Stanley Cup finals to the Canadian Embassy in Peru. And that is sort of the first direct-to-home satellite. So we introduced that. Our advanced communications satellite looked at a lot of the satellite systems that are now used to distribute internet to via satellite. And my one cousin is quite appreciative of that. Is a security officer for an accounting firm. He has to have internet access 24/7, and satellite is the only way he can get it at his place up in Michigan. So he can be up there and still be in communication for his job. And we actually received, we the Canadians shared an Emmy, technical Emmy for the Hermes Communications Technology Satellite. And do you have any questions?
What got you interested in pursuing this particular field and being in NASA? I'm out of curiosity.
Basically, I was trying to finish a PhD actually in theoretical solid-state physics. And the market for physicists had dropped out completely. I mean, it was bad enough back then you had to print out your resume and type up a cover letter and mail it physically to apply for a job. Nowadays, you do that all electronically. Nowadays, a physics professorship opening up, we get like 600 applications. Back then, they would get 2,000 applications. So basically, it was like, I'm not going to get a job in my field. So I started looking for other jobs. And in the early 80s, the job market was pretty bleak. I was about to apply for a job in Detroit as an assistant manager at Little Caesars when I got called into an interview at NASA. I was doing interviews at Michigan State where I was going to college at the time. I didn't was able to get an interview there, but I was called in. My future boss was looking for physics professors because none of the electronics engineers knew anything about vacuum tubes. And they didn't have as much electromagnetic knowledge training as physicists did. So I got called in for the job interview and offered the job. And became an engineer because NASA would pay you $3,000 more a year if you called yourself an engineer than if you called yourself a physicist. And jobs were hard to come by. In fact, I got a call from the NASA personnel department saying, you don't really want to come to Cleveland, do you? It's like, I want to play in Detroit. Why wouldn't I want to come to Cleveland? My brother worked for what was then Shell, Ohio, at Shell of Ohio, there. So he was already in Cleveland. So it was a very easy choice to do that. But basically, I hadn't been looking for NASA otherwise. My original plans had been more to become a college professor. I did at one point become a visiting assistant college professor at Indiana University, Purdue University at Fort Wayne. But that was very much a one-year appointment. A friend of mine actually had been hired the year before for what was supposed to be a permanent job and was leaving because the job didn't become permanent. And that's what got me into working at NASA and traveling wave tubes. I know at one point I actually, shortly after I got hired there, they were passing around a thing on personnel. And at that point, NASA employed 7 alien scientists. I was going, I should take this and sell it to National Enquirer. Actually, my boss at one time had been one of those alien scientists employed at NASA. He was from Planet Germany before he became a naturalized citizen. Any other questions?
Yeah, there's one that just got in the chat. Are the inputs and outputs 50 or 75 ohms like in broadcast?
They actually are generally waveguide in most of our tubes. Otherwise, I think they tend to be 50 or so coax. It can vary. We've also worked for DoD, and a lot of their ones, they do use coaxial outputs. In our cases, they are generally waveguide.
Quick question just for attendance sake. The 612 number that's calling in, could you quickly identify yourself just so we have that for our attendance purposes?
Scott Todd.
Gotcha.
I can't log in there. I couldn't log into any of the normal chat channels. I mean video. The Zoom or the Google meeting. I couldn't get in on either one of them.
Sure. One question I had, just on a really rookie level, what all does the Glenn Research Center research other than your work? Well, there's lots of other facilities out there. I was sifting through which one handled Minnesota stuff, so got curious what the breakdown was.
Well, the breakdown for areas by region is who's ever nearest the region to a large extent. And we're the Midwest Center. But our research started in aeronautics, We actually worked on propellers at one time in piston engines. A lot of the early work was actually on figuring out why the B-29 engines tend to catch on fire. But we also have a facility right across the road from me. We have the Propulsion Systems Laboratory. They can run any jet engine in the world, even with its afterburner on, at simulated altitude and speed, and measure to less than a pound what the thrust levels are. And they've since modified that to add on the ability to dump high ice water content into a jet engine, because that can sometimes cause a jet engine to fail. In some cases, it's caused all the engines on a plane to fail, typically a two-engine plane. And that has now been used. Honeywell had an engine that had failed on a flight in Canada. The Canadians had a good idea what the weather was. Apparently they should turn it back on because it's all landed properly. But they actually were able to reproduce the conditions and with a bunch of extra instrumentation at it, measure what was happening. We did a lot of early rocket research, particularly on hydrogen and oxygen rockets at our center there. We also have a 500-foot drop tower. We can give you 5 seconds of microgravity. There, we have some shock tenders. A lot of the work testing on what happened to the Challenger when it was hit by that piece of foam was done at Glenn by firing little pieces of foam at parts of the space shuttle and finding out what happened. We have a facility out about an hour's drive west of town near Sandusky. That has the world's largest vacuum chamber. A lot of rockets get taken there to test to see if the shroud will come off properly, because quite a few satellites have been lost because the shroud holding the satellite on for launch doesn't come off. And the satellite has to go down with the upper stage of the rocket. That one can also test for sound levels there. Right at the top of a rocket, you're not in a quiet area like at the back of a jet engine. The sound levels are really enormous, but they can run the test for that there in that facility too. You actually could play a basketball game inside the vacuum chamber. It's that large. When I first was there, they said it was the largest one in the free world, but after the fall of the Berlin Wall, they discovered it's the largest one in the world. We also have a facility where you can test upper stage rocket as though it's at 100,000 feet. Well, it's operating. They can pump that fast with the vacuum to hold the vacuum down to maybe about 5–10% of atmospheric pressure while firing an upper stage rocket at that facility. Those ones tend to be loud. We've got about 10 square miles of what used to be the military set it up as an explosives production plant in World War II. It was Plumbrook, was now the Armstrong Test Facility of NASA Glenn Research Center. And we have a variety of other things. We do a lot of research on solar cells and the use of Stirling generators with for radiothermal. We're trying to replace the thermoelectric generators that are used with the nuclear fuels on space satellites, the deep space ones where they can't get solar power to operate them. Replace that with a Stirling engine, which is considerably more efficient, so we can get considerably more electric power out of the same generators. And I know for a Cassini in the 90s, the estimate for electricity charge was $1 million per watt. And in Earth orbit, it's only about a few $1,000s for solar cells. Mostly it costs quite a bit to make the solar cells to fly up there and launch the solar cells. So it does a wide variety of research. We used to have planes that could fly out and do the parabolic loops to test zero gravity operation. I know we got that one because the previous owner fled to Cuba to avoid arrest for fraud, insurance fraud. I mean, he had an insurance company. It was very fraudulent. They seized his aircraft and said, oh, here's one you can use. And one of the areas our media group is working on is delay tolerant networking. And we've done other work with the Internet Engineering Task Force. It turns out that the original internet protocols could not handle, if you could send a lot of data between the time the first message went out and the next one, it caused problems. Now, these are very large amounts of data, but satellite communications has a long delay time, and the fiber optics transmit a huge amount of things at a time. And they actually were hitting up to cause problems that way. There was so much data en route already by the time we got the message back. They had to modify the protocols to handle that. And at various times, we've also done studies on wind power and coal burning. Any other questions?
Anything else, members?
I don't have a question, just a comment of, wow, that is just mind-numbing to think about all the things that you explained, Dale. Thank you so much. That's really eye-opening. I'm a former military member, so I can appreciate some of what you're saying from a different perspective. So thank you.
Yes, I know we're heavily involved in helping downsize them. One of the early satellite ones, we have a cutout, have half of it, half cutaway cutout of it. And it basically is a desktop size thing. And it produced about the same power at the same frequencies. We were later working with the military on a miniature power module, microwave power module, that was roughly the size of a cell phone. That also produced a couple hundred watts of power. That one actually needed liquid cooling, although I believe the Northrop flies one of them, has flown one of them for the synthetic aperture radar on LRO.
Another rookie question, if I can ask one.
Yeah.
Without asking anything too sensitive, what's your relationship with these newer private sector entities, SpaceX and the like?
I haven't had any particular direct contact with them. I do have a lot of things with the private companies that involved in the traveling wave tubes and such. At the higher frequencies, there currently, last I knew, there were 3 companies that did it. And when I did the market survey on them, the Japanese company said, we only do, it's part of NEC. And basically their tube producers is not really deciding to make a profit. But if the government asks them to make some tubes, they make them. The Japanese government asks them to make some tubes. Otherwise, there is Thales in Europe, and well, it just changed its name. Got bought out as a separate entity from L3 Harris, then in Torrance, California. There are some other companies that make them for military use, but not space ones. And in fact, we were recently honored. The space traveling wave tubes in our work were inducted into the Space Technology Hall of Fame. Roughly, it was supposed to be a 2020 session that the induction was done. I was getting all ready to fly out to Arizona for it when we weren't allowed to travel anymore. And at one point, we were doing some classified work. I had a security clearance for a while, but after 10 years, I hadn't actually learned anything secret. So NASA decided not to pay to renew it. I know we also do some work with helicopters at NASA Glenn. So I've not really been involved in that at all. Any other questions? I do know one of the big things that tended to get NASA in Cleveland, well, it was the NACA then. Ohio was a big engine area. The other side of the airport from NASA was where Ford used to make all its automotive engines. TRW was also a big company in town, and GE still makes most of their jet engines in Ohio. So these were a big reason for the area being there. Plus, they offered a cheap electricity deal. We ran for run our wind tunnels at night. And we have several major wind tunnels there. The early transonic wind tunnels were actually developed at Glenn, be able to operate. It turns out it was before that they had good ones that were fairly low speeds, below the sound barrier. And they also have good wind tunnels that operated well above the sound barrier. But right around the speed of sound, they had problems with their wind tunnels.
Imagine that.
Yeah, getting them to produce the right things. I know we have an icing research tunnel too, where we put ice wings. It took them a couple of years to get the right formula for building ice properly onto wings. But that is a heavily used wind tunnel here. I did see pictures once of one up in, I think, the University of Minnesota that they use for icing research too, but only in the middle of the winter. They just put it outside to get cold enough. At one point during World War II, they built the largest air conditioning unit, or refrigeration unit. Carrier himself came out in person to help develop it. That was for our altitude wind tunnel, but it was also used in our icing research tunnel. So we do our icing research in the middle of the summer.
Hearing nothing else. All right, sir. Thank you very much for your time. This has been an extremely informative discussion.
Thank you very much. I've enjoyed being here.
Thank you, Dale.
You're welcome.
Have a good weekend.
Thank you.
Thanks, everyone, for joining.
Thanks, Taylor.
Thanks, Taylor. Appreciate it.